Hi, welcome to section 5.2, Precalculus Inverse Functions. So we're going to be finding some inverse functions today. I want you to warm up, however, by doing a composition of functions, which are the first four, and then I'll go through some graphical ideas for the next two graphing examples. So go do these and I'll show you the answers. Okay, so we have f of g of x. So we put the g function into the f function. And if you simplify, you should get this. Double check your errors. This one, we're going to put the h into the f function. And remember that when we do this, wherever we see this circle here, we're going to put a left bracket. That means we're going to put the h function into the f. And that's what we did there. And when we simplify, we get negative x. Now you got to check your domain for that one too. That would be for x less than or equal to 4 because when we started, that's what we needed. So the inside function we had to deal with. Then the third one, put the f function into the h. And we did that again. And then at the end, our domain is limited by negative square root of 8 to square root of 8. And then the fourth one is that we try to put 3 into the k. Well, you can do it a couple ways. G of k, you can put this in, and then you can apply the 3 at the end, or else you can just put the 3 into the k function, 3 into the k function, and then evaluate that value from g. So you plug it in there. I did it the long way kind of there. Okay, so that's the introduction. Moving on to the arithmetic of functions. We've done this before, but I think it's good that you see how to plot these points and add one on top of another. So for instance, if I have two functions, f and g, and I want to add those two together, what I need to do is really you add the y coordinates. So as you go from x to x, you go and find the y coordinates and you add them together. So for instance, well, here I don't have the circle function. This is a semicircle. You need to recognize that equation as a semicircle. What happens here is that I have the line y equal to x. It starts, or the semicircle starts right here. This y value is 0. This y value is negative 2. And if I take and I add those two together, 0 plus negative 2, I'm going to get negative 2. Now, what are the y values of each of the functions here at negative 1? Well, if I go up here, this is approximately 1 3/4. This one's negative 1. So if I take 1 3/4 and I subtract 1, I am going to get this point right here. I'm trying to make the ones that I'm actually plotting bigger. Then if I go here at 0, this is 0, 0. This is 2. 0 plus 2 is 2. And I go to 1. This is 1, and this is about 1 3/4. So I bump this up by 1, and I'm going to get this point here. Hopefully you can see what I'm doing. This one has a y value of 1. This one has a y value of 1 3/4. Plot that point. Then here, I got a 0 here, and I got a 2 here. So if I add those two together, I get that. Now, if I connect this, I'll probably get something like this. And you probably want to take your calculator and see if you can add these two and see what it would look like. I'm going to venture a guess it's going to look like this. It might have something else out here, but since this is undefined, then it should only show up between negative 2 and 2. So take on the domain of whatever you have here. The smaller the domain for one of the functions, well, that's what you're going to have to deal with. Why don't you try this one? I'll get you started. This one's 0, 0, and this is 2. 0 plus 2 is 2. Try this one. Oh, we got a couple here. F plus G. So do these two first, and then we'll try these two. So I'll come back, pause, and try to plot this. So there's my G. Looks like the top there. Okay? So what we want to do now is take F plus G. So I'm going to be taking this bottom part of the semicircle. Remember, recognize that these are semicircles. Positive is the top part, negative is the bottom part. So now I'm going to be taking this line and adding in this semicircle down here. So if I start here, this would be 2, oh, same thing. Why don't you try it and see what you get? Aha, what'd you get, a heart? I got a heart. So that's what I'm looking at. And so with this, just make sure that you plug in these points and see where they come from. Once again, On this function, it's about negative 1 3/4 or up there someplace, and then I'm adding a positive 1. So I'm going to take this point here. And then here I'm going to have 0 plus negative 2, which is negative 2. This one's symmetrical here, and then this one's symmetrical here. So I get my heart. And if we look on our little navigator here, there is the heart. So when you want to, for Valentine's Day, you can send your sweetie a love heart. Isn't that nice? A mathematical love heart. Okay, let's get back into inverse functions now. Okay, so if we talk about inverse functions, definition of an inverse function, let f and g be two functions such that f of g of x equals x and g of f of x equals x. What happens with this is that if I have my x's, and this goes back to the mapping from last section, and I want to take them over with some f function, that means in here I'm going to get f of x. Well, what I want to do then is I want to take them back and bring them back where I started from with my g function. So that means that I'm going to take these x's, apply the f, and then apply the g function, and that's going to get me back to x. And how we write this as a composition, this would be f of x, and then we're going to take and we're going to apply the g function to whatever we got out from that. So that's g of f of x, and that's going to bring me right back to where I started from. So with inverse functions, that's what we want. And so to do this, well, let me do the notation here first. This is f inverse of x. This means the inverse. This does not mean 1 over f. It's unfortunate notation that they've used this because you've learned this as putting it as in the denominator, but it does not mean that. It is just language. So this means f inverse. This right here means f inverse, and that's what we want to be able to deal with. So if we look at this, how do we find the inverse? Well, first of all, we go y equals 3x minus 1. I hope that you've done this before, but I'm not sure. X is equal to 3y minus 1. What we're doing is we switch our x and y's. And then you go ahead and solve for y. So when I do this, I'm going to solve for y. I'm going to add 1 to both sides, and then I need to divide by 3. So then I get y equals x plus 1 divided by 3. Now we're not done because we have to tell everybody what this is. What this is f inverse. So it's f inverse of x is equal to x plus 1 over 3. Now, really, all we're doing with this is we're switching the x's and the y's, switching my inputs and my outputs. So let's look at number 2. I have all these x inputs, and then I have all these y outputs. Well, to find the inverse, all I do, and these are just points, all I do is I switch them around. So this would be 3, 2. Switch them around. 1, 5. 2, 6, and 2, 3. Now the question is, first of all, did I have a function? Well, if I look at this, the x's never double up. Yes, that's a function. What about my inverse? 3, 2, 1, 5, 2, 6, 2, oh. My inverse is not a function. We have to pay close attention to this. So this really is not an inverse function. I did switch it around, but it is not a function. So we'll talk about that a little bit later. So let's switch x and y here and see what we get. Why don't you try it, and I'll pause this. Oh, no, I need to show you this one. So if I have y equals 5x over x plus 2, now I want to switch the x and y's. So x is equal to 5y over y plus 2. Now, how to solve for y? There's 2 of them. And this gets a little bit tricky, but this is a great technique, and you need this in calculus too. I cross multiply. And then I can distribute xy plus 2x is equal to 5y. I want to isolate my y now. And how I do that is I get the y's to one side. So put all your y's on one side. So this would be xy plus 5y is equal to 2x. Some of you are going, okay, I think I know what to do now. And I'm going to go up here. See, y's in common. I can factor it out. So then this would be x plus 5 is equal to 2x. I'm out of room here a little bit. Solve for y. So y is equal to, I have to divide both sides by x plus 5. 2x over x plus 5. I'm not done. I have to write f inverse of x is equal to 2x over x plus 5. Okay, so I have to worry about my domain here. X can't be 5. Negative 5, sorry. X can't be negative 5. So what are we doing here? We're finding inverses. With inverse, we switch x and y's. And then we solve for the y's. So looking at this situation, solving for y became a little bit tricky, but I think you can sort that one out. Okay, let's go to the second page. See where we're at. Okay, we want to find or graph the inverse of the cube root of x minus 2 minus 1 and try to figure this out. Well, we are switching x and y's. We want to switch the x and y's. So what happens now is that when we switch x and y, we're going to reflect over this line. This line is called the y equal to x line. Some people call it the identity. They do that in the Stitz-Ziegler book. Okay, so this is the identity. And what we do is we reflect, since we're switching x and y's, we reflect over that. So for instance, if I take this point here, which we call 3, 0, to find the point on the inverse, I get 0, 3. So it's going to be this one here. And here, oh, look at it. If it crosses the line, I switch x and y, it's still the same point. So that's kind of nice. This one here would be 1, negative 2. Switch x and y, I get negative 2, 1. Hopefully you can see what's happening here a little bit. And then here, this point is 2, negative 1. So I get negative 1, 2. I'm not going to write that in there because it gets too squeezed. So what happens with this, I'm going to get something like this. And I believe it goes off like this. Okay? So that's what that would look like. And if I did a pretty good job, if I connected these 2 points, they would be perpendicular to the y equal to x. If I connect these 2 points, that line would be perpendicular and that one too. Now my screen seems a little stretched here. You might have to go zoom square if you graph this on your calculator. If you go zoom square, it makes sure that these units or these blocks are square so you don't get that stretched out big screen TV, somebody's face looks wider than a house kind of deal. So think about zoom square and then that will give you a better picture. Okay, moving on. One-to-one function and horizontal line test. Horizontal line test. What we can do is we can test a function with a horizontal line test to see if its inverse is a function. So remember that I just graphed this up here. Does this one look like a function? Absolutely it does. Well, we get a function if it's continuous like this if I satisfy what we call the horizontal line test. So any horizontal line that I draw, if it intersects exclusively in one point, or at most one point, then we can find the inverse. And the inverse is a function. If we ever have it cross over more than one point, then it would not be a function. So it's looking at the original function to talk about the inverse function. I'll show this with an example in a minute. And then we also have something that's called a one-to-one function. If you have a one-to-one function, then each value of the dependent variable corresponds exactly one with the independent variable. So like when we had a function before, each x matched up with only one y. Well, if it's one-to-one, each x matches up with only one y, and each y only matches up with one x. So you don't have any duplication. Now, with this, if it's a continuous function, not continuously. If we have a continuous function, that means that it has to be strictly increasing or strictly decreasing to be 1-to-1. Okay, so let's look at this for a second. This example, is this 1-to-1? This is a quadratic, x minus 3. So inside parentheses moves right 3. Parabola. Boom, boom. Well, is this strictly increasing or strictly decreasing? It is a continuous function. Continuous means that I never lift up my pencil. But it is a continuous function. And if I draw a horizontal line, it fails. So then my inverse, or the inverse of this, is not a function. Right? And in fact, if you flip this over the y equal to x, you would see that it'd be something like this. Okay? So this is not 1-to-1. No, it is not. 2 reasons. It's not strictly increasing or decreasing, and then it does not satisfy the horizontal line test. Okay, is y equals x cubed minus 3 1-to-1? Well, this would be a cubic, move down 3. Is it strictly increasing or strictly decreasing? Yes, it is. Does it satisfy the horizontal line test? Yes. If I take any horizontal line, it will only intersect in one point. So the inverse with the horizontal line test is a function and will be a function. So this is yes, it is 1-to-1. Now, when I say continuous, what you'll get is situations like this. If I get a bunch of points, is this 1-to-1? Yes, this would be 1-to-1. But if I put a point right here, well, that's not a function. So if I put a point over here instead, sorry about that. If I'm dealing with data points, now this one would not and my lines are terrible here with the drawing on here, but my line would, these points would not satisfy the horizontal line test because I have more than one point through there. So this would not be 1-to-1. Is it strictly increasing? No, but it's data points. It's not continuous. So that goes under a different category. Okay, so let's look at this here. Now, the last situation, and we'll go through this more in class too, but this last situation says prove that these are inverses of each other. So I already switched the x and y's and did all that. If we want to prove, this is what I asked you to do before, how do we prove? Well, we must show that f of g of x, this is from the very first statement that we had at the beginning of this, is equal to x, and g of f of x is equal to x. So here's my intro. Tell us what we'd have to show. Then, body, go ahead and show it. So f of g of x, so I'm going to take the g function and put it into the f function. So wherever I see the x, I put that. And then I'm going to put the 2x plus 3 inside. This cancels nicely, so I get 2x over 2. And if you do this, make sure that you do enough of this, but this comes out to be x, which is what we want. Then we also must show that g of f of x is equal to x. So now I must put the f function in the g function and see how that sorts itself out. So I take the g, put big parentheses, and what do I put inside? Well, this is going to be x minus 3 all over 2. Now, if you notice, these 2's cancel. So this is x minus 3 plus 3. Don't just cross out everything in one line. Rewrite the line, and now this is equal to x. So now we did the intro, we did the body, and then we want to conclude. So since f of g of x is equal to x, and write this as separate statements. Don't put it in one package. G of f of x is equal to x. F and g are inverses. Seems a little redundant, but go ahead and do this. Tell us what you're going to do. Go ahead and do it, and then summarize what you just did. Okay, now what you can do for yourself is summarize how to find an inverse. We want to do it algebraically and graphically. Remember that this we reflect over y equal to x. This one we switch x and y and solve for y. One-to-one functions. Well, that would be as if they're continuous functions, it's strictly increasing or strictly decreasing, and then you must prove. Thank you very much. Sorry about the length of this. Have a great day.